So hello, we're back again with another lecture for statics of rigid bodies. So we'll still be dealing with force vectors. So previously, these are our chapter objectives, and previously we already covered how to add forces and resolve forces into their components using parallelogram as well as the triangle law. So to continue our lesson on force vectors, now we will learn to express force and also position vectors in their Cartesian vector form, or CVF. We'll be learning that later. And also to explain how to determine the vector's magnitude and the direction. So we will compute for magnitude, and we will also determine the direction or the angle of the vector. First, we will be applying the principles in 2 dimensions, and eventually we will extend that into 3 dimensions in 3D. Also to introduce the dot product in order to use it to find angle between two vectors or projection of one vector into another. So for this lecture, I think we there's a chance that we might not reach this one, but we will see. So we'll continue with addition of a system of coplanar forces. So let's talk first about scalar notation. So when a force is resolved into two components along the x and the y axis, the components are then called rectangular components. So from our previous lecture, we learned how to resolve first we learned how to add forces and determine the resultant force, and then from the resultant force we also learned how to find the components along specified axis. So from that, the axes are not really perpendicular to each other, but this time we will be looking at axes that are perpendicular to each other, particularly the x and y axis, and these components will be termed rectangular components. So for analytical work, we can represent these components in one of two ways: either the scalar notation and the Cartesian vector notation. So first, we have the force F here in boldface, so that means it's a vector, and what we are going to do is to resolve this resultant vector, this vector F, into its x and y components, which is, let's write it down as f of x, fx and fy. Okay, so as you can see, fx would be along the x-axis and y would be along the y-axis. That's why we call it rectangular components. It's basically applying the parallelogram law, but since they are perpendicular to each other, what we are going to form is a rectangle, thus rectangular components. Alright, so we also have here an angle which will determine the direction of our vector. So this is force vector F, which is theta angle from the x-axis. So that is the direction of our vector. So it's also important that we find what is the value of this angle, whether it will be given in the problem or we have to solve for it. So as you can see here, we can solve for the magnitude. Take note, this is the magnitude of the component in x. That would be the magnitude of f multiplied by the cosine of the angle theta. So cosine is equal to adjacent over hypotenuse. So that's why this is the adjacent side. This is the adjacent side is your f of x. Sorry, not f of x, but fx. Okay, so in order to find the magnitude of fx, if the magnitude of the resultant force is given and the angle is given, we can simplify it by multiplying the magnitude of f with the cosine of the angle. And on the other hand, so to find the component in the y-axis, which is fy, we multiply the magnitude of f with the sine of the angle. So sine is opposite over hypotenuse. So this angle, this is the opposite side. Okay, so opposite over hypotenuse. So the sine of the angle multiplied by the magnitude of the force of the resultant will give us the magnitude in the y. The magnitude of the force component in the y-axis. That's one way. Another way is if we can use ratio and proportion. Okay, so I believe everyone is particular with the Pythagorean theorem. So if you have two perpendicular sides, the hypotenuse would just be equal to the square root of the sum of the squares. So that would be a squared plus b squared will just be equal to c squared. Okay, so we have here this ABC triangle. So this ABC triangle denotes the ratio of the sides to the hypotenuse. Okay, so if this is our resultant force, and it is proportional to the measurement of the hypotenuse or c, so its components in the x and y will also be proportional to the length of the sides of this small triangle here. Okay, so since f of x is proportional to a and f is proportional to c, we can find the magnitude of fx to be equal to f multiplied by our ratio. Okay, so since we're looking for f, we will be using the side which is proportional to f, or sorry, fx, or parallel to fx. In this case, that's a. Okay, so don't be confused. Sometimes a will be written here, b would be written here. Just keep in mind that you will be multiplying the magnitude of the force to find the x component, multiply it with the proportional side or the parallel side. Okay, in this case a is parallel to f of x, so we use a over c. Okay, so to find fx, we multiply f with the proportion a over c. For fy, the same thing goes. So in this case, look that our sign convention would be the typical sign convention of the xy coordinate system. So in this case, if you can see, our fy is going down, so that will have a negative sign convention. Okay, so we will have negative f multiplied by, in this case, this would be b, the proportional side, over c. Okay, so the idea is to multiply the hypotenuse of the resultant force with the proportional side of the smaller triangle divided by the hypotenuse, of course. So it's just ratio and proportion. So I know maybe some of you will not be very comfortable with that, but if you want, you can still solve for the angles here using trigonometry, but that would take additional time. So I advise that you try to get comfortable with this ratio and proportion when it is given in the problem. So as I said, there's no problem if you want to take the angles used and then use the first method. You will also arrive in the same answer, but the question here is which would be the faster faster way to solve it. So these are just two methods to find the rectangular components. So the next one would be Cartesian vector notation. So what is Cartesian vector notation? So when we want to express a vector into its Cartesian vector form with its components, we will be introducing the concept of unit vectors. Okay, so what is a unit vector? It's basically a vector with a direction and a magnitude of, since it says unit of 1. Okay, so a vector with a magnitude of 1, that denotes a directional axis. Okay, so as a standard, for now, we will be doing 2 dimensions only. So right now, maybe you won't appreciate the help of this Cartesian vector notation since we are in 3D. You are better off using our first two methods, but this one, I advise that you try to be familiar with it because this will be very useful. You will appreciate this method when we go to the 3-dimensional in 3D. So for now, as a standard, we use I, J, and K. Okay, so I, J, and K unit vectors. So I is to the x-axis. So if we will be writing the Cartesian vector form of a vector, I, the direction I would be, the direction of unit vector I would be for the x-axis. Okay, so please keep that in mind. The direction for the y-axis, or the unit vector for the y-axis, would be the unit vector j, and for the z-axis, the third axis, so it is not shown here. As I've said, we will be dealing with 2-dimensional first, and for the third dimension, that would be, we will be using the unit vector k. Okay, so this is how you will write the Cartesian vector notation of the vector. If you're given a vector f here, you're given angles and magnitudes of the rectangular components, we will write it as such. I hope you can see which one is written in boldface and which one is in italics. Okay, so here f, the vector f written in boldface, so it's a vector, is equal to our magnitude. This is not in boldface, this is italic, so this is denoting magnitude. The magnitude of the component in the x-axis multiplied by the unit vector I. Okay, so this one is denoting the magnitude, and the unit vector we introduced is denoting the direction. So in this case, this would still be a vector since we learned from our first meeting that the vector has a magnitude and a direction and a line of action. So for the x component, we'll be using the unit vector I, and that would be plus. So if you will recall, this would not be just algebraic addition. Okay, this would be vector addition. Okay, so you will use your triangle law, parallelogram law, etc. for this. So for the component in the y-axis, that would just be the magnitude of Fy. We already have methods in determining Fx and Fy from earlier. So here Fy multiplied by the unit vector in the y-axis, or in the y direction, which is j. Okay, so you can imagine further that when we arrived in 3D, you will just need to add here the Fz, or the component in the z-axis, and that would be plus Fz, the unit vector k. Okay, so please remember, this is how you write your vector in Cartesian vector notation, or Cartesian vector form. So in the following problems, when you are asked to write the vector in its Cartesian vector form, or CVF, this is our expected answer in this format. Okay, so for coplanar force resultant, this would be involving forces more than 2. Okay, so in order to add those forces, we need to first each force resolved into x and y components. Okay, so we will do what we did, or what we discussed earlier. For, let's say, 3 resultant force, we'll break them down and find their x and y components, and then the respective components are added using scalar algebra, since they are collinear. So we have here force 1, force 2, and force 3. So you can imagine, in this Cartesian vector, in this Cartesian coordinate plane, we can resolve F1 into its y and x components. That's same for F2, y and x components. Same for F3, also have y and x components. So if we get the component of F1 in the x, we get the component F2 in the x, we get the component of F3 in the x, we can add those components, all the components in the going in the x-axis, because they are collinear. That is just scalar algebra. We can just add or subtract the value or the magnitude of these forces, since they are in the same line. Same goes for our y-axis. So the component of F1 in y, for F2 in y, and F3 in y, also you can add by just using scalar algebra. We will arrive in an answer. We will have a single x and y component, which we can further resolve, or we can find the resultant, and that would be the resultant of this coplanar force system. Okay, so the resultant force is then formed by adding the resultant components using what we learned, the first thing we learned in this subject, parallelogram and triangle rules. Okay, so as you can see here, this is F1, F2, and F3, and we resolve them into the so-called rectangular components. So we have F1x, F2x, F3x. So notice here that F1x is going to the positive x, as well as F3x. F2x, on the other hand, is going to the negative x direction. So if you add those, that would be F1x plus F3x minus f2x. That's the scalar algebra for it. Sorry. Same goes for y. We have f1y going to the positive y direction, f2y going to the positive y direction, and f3y going to the negative y direction. So if we sum this up or use scalar algebra, that would just be f1y plus f2y minus f3y. And the answer would be a force in the x direction and a force in the y direction, which again we can find the resultant for that as well as the direction. Okay, so the resultant force is formed by adding the components using parallelogram law. In this case, since they are rectangular components, we can simply use what do you call it? It's the Pythagorean theorem. Okay, so writing down our the forces F1, F2, and F3 into their Cartesian vector notation. For F1, that would be F1x I, okay, in the x direction, plus F1y j. Okay, so this is a plus sign since the components of F1 are both going in the positive x direction and in the positive y direction. For F2, we can write it as negative F2x. You can see here it's going to the negative x-axis. That's why it's negative F2x, still the unit vector I, plus F2y, the unit vector j. So F2y is going up, so that's why it's a plus. Okay, so at this point I just want to emphasize here that you when you are drawing your free body diagrams, when you are drawing the diagram for your forces, please make sure that you are consistent with your sign convention. So what we are already taught in our geometry classes, that is that right the right side of the x-axis would be the positive. For the y-axis, going up would be positive, and reverse is true for the other direction, going down for y and going left for x. So it's important that you stick, or to avoid confusion, maybe for now we will stick with that sign convention. But what I want you to understand is that you need to be consistent with your sign convention. So in this case, we decided that x going to the right is positive, y going up is positive, and the opposite for the negative direction. Okay, so for F3, the x component is going right, that would be positive, so F3x I, and the y component is going down, that would be negative F3y j. Okay, so please always remember I is for x direction and j is for y direction. So in order to find the resultant of this coplanar force system, F1 plus F2 plus F3, this is vector addition of forces, we simply add all the forces that is in the same direction. So in this case, as you can see, all the x components are in the same direction. That's why we will just add them. So that's F1x minus F2x plus F3x. So it's better that you write it down in this way. You can just see the components here, the magnitudes of the components in the x-axis. You can write it down easier, and all of those would be multiplied by the unit vector in the direction of x, which is I. Same goes for y. So f1y plus f2y minus f3y. Okay, so it's very important that you know how to express your forces or your vectors in their Cartesian vector form. I know it's simple addition, but be very careful of the sign, which is negative, which is positive. So it's better to write it down and learn how to come up with this Cartesian vector forms. Alright, so our resultant force would just be equal to the summation of forces in the x direction, that's the resultant in x, multiplied by I, plus the summation of forces in the y direction, that's resultant in the y, multiplied by j. So we can represent the components of resultant force of any number of coplanar forces symbolically by algebraic sum of the x and y components of all the forces. So those are just 3 forces. You can also resolve 4 forces or 5 forces or even how many forces you like. So this is our formula. So for the resultant in x, that would just be the summation forces in x, and for y, that would be the summation forces in y. So by the Pythagorean theorem, we can solve for the resultant, the magnitude of the resultant, by finding the square root of the sum of the squares of the components. In this case, we have frx and fry. So frx squared plus fry squared, the square root of that would just give us the resultant. So this is our resultant force, Fr. This is the component in x. This is the component in y, Frx and Fry. And obviously, there would be a measurement of angle either in the x-axis or in the y-axis. So for this one, we measured it in the x-axis. That would be, let's name that angle as theta. So this theta can be find by using trigonometry. If we have here an adjacent side and an opposite side, so that would just be the tangent of the angle. So tangent of the angle is equal to the opposite over the adjacent. So we can solve for the theta or this angle, this one, by getting the arc tangent of opposite over adjacent. That would be y over x. So force resultant in y over force resultant in x, the absolute value of that. Okay, so the absolute value would be the arctangent of the absolute value of y over x would be equal to this theta. Okay, so we solve for the component in x-axis by doing the summation forces in x, and the component in y-axis by doing the summation forces in y, and we find the angle by getting the arctangent of y over x. So by that, we have our vector and its direction. So this is just a summary of the steps that we take and we do when we are solving for rectangular components. Okay, so I'll just let you read through this. For us to better understand how we apply this force vector principles. Let's try this sample problem. So what we need to do is to determine the x and y components of F1 given here as 200 newtons and F2 given as 260 newtons acting on the boom shown. So our task is to express each force as a Cartesian vector. So if you can recall, the Cartesian vector form is the one with the I and J unit vectors. Okay, so our these are the directions of each vector. Force 1 is 30 degrees from the positive y-axis, while force 2 is in the fourth quadrant, and it's in the positive x and negative y direction with a 5, 12, 13 triangle with the ratio of the triangle side is 5, 12, and 13. So let's try to solve this problem. Okay, so let's label this one as, first we need to write our given. So this is our given. We have here force 1, so it's a vector, force 1, which is equal to 200 newtons, and it's in with an angle 30 degrees from y. This is force 2. This is 260 newtons, and it has a ratio of the sides of 5, 12, and the hypotenuse 13. So this is our, so for this problem, let's use the common convention in the x and y coordinate axis, where this would be the positive x, this direction, this would be the negative x. For y, going up is positive and going down is negative. Okay, so basically this is what you need for your given. You need to be able to illustrate the problems and the vectors. Now we are looking for what is the problem asking. Required. So what is required is the Cartesian vector form of each vector, right? So the Cartesian vector form is something like force equals f x I plus f y j. So if you notice, we need to find fx for each force, f1x, f1y, so let's write that down. So we need f1x, f1y. Also we need f2x and f2y. Okay, so for the solution, let's pick which would go first, but obviously we will solve for the components of f1 first. Okay, so for f1, the magnitude is 200 newtons. We are trying to find the component in x, which is obviously this is your f1x, and it's in the negative x direction, while your y is in the positive y direction. So this is your f1y. Okay, so what does f1x look like? f1x would be, so this is the angle 30 degrees, and this is f1x opposite it. So what we will write is, since it's going in the negative direction, it would be negative f1 multiplied by the, this is opposite over hypotenuse, so that would be a sine of our angle here, which is 30 degrees. Sine 30 degrees is 1/2. So this would be our equation for f1 x. So for f1y, on the other hand, so f1y happened to be adjacent the angle. So for this, and it's in the positive direction, so we'll be writing it as f1, the magnitude of f1 multiplied by the cosine of 30 degrees. So I hope at this point you won't be confused, because in the derivation of the equation that we had earlier, the angle is measured from the x-axis, but this time it's measured in the y-axis. That's why you just need to look for which is the opposite side and which is the adjacent side in order to identify what trigonometric function you must use. So here for f1x, we use sine, since f1x here is opposite the angle, and the same goes for f1y, which is adjacent the angle. If it's the other way around, if the angle is measured here in the, that's obviously 60 degrees, so we can use 60, that would be negative f1 cosine of 60, and f1y would be equal to f1 sine of 60. That would be the same. Okay, so let's solve this equation. We have f1x is equal to negative 200 newtons times sine 30, which is 1/2 or 0.5. Our f1x would be negative 100 newtons. So there will be two ways how to write the value for f1x here. Either we keep it as negative 100 newtons, or we can write positive 100 newtons but going to the left, which means it's negative. Okay, so we can write it down that way. So for the component in the y direction, that would be f1, that's 200 newtons, cosine 30. So let's plug it in our calculators. So cosine 30 would be equal to square root of 3 over 2. So that would be 200 newtons. Please don't forget to include the units in your calculations. Okay, so that would be square root of 3 over 2, and if you plug that in your calculator, that would be equal to 173 approximately 0.205, or I will round it off as 21 here, 21 newtons. So we can write it as such: positive 173.21 or 173.21 newtons, and it's going up. Okay, so to write the Cartesian vector form of force 1, so remember, when you're writing vectors, that should be in boldface. So for here, I will just write it this way. So f1 is equal to, that's negative 100 I plus 173.21 J so I will enclose this in parentheses and write the unit newtons. Okay, so this is it's pretty much in its Cartesian vector form. So for f2, we have here look at this, we have a ratio. Okay, so for the component in y, that is in the negative direction of y, that's f2y, but this time x is the one in the positive direction, that's f2x. So we'll be looking for f2x and f2y. So we learned earlier about ratio and proportion, proportion, using the ratio of the slope of the triangle. So f2x here would be equal to f2, that's positive, so f2 multiplied by what ratio? So we are looking at the same side, which is proportion to that the side we're looking for, or the one that is parallel. So this, from this, 12 is parallel to our f2x, so we will be using 12 over the length of the hypotenuse, which is 13. So for f2y, we will be using the side which is parallel, which here is 5. Okay, so since it's going down, we will use negative the value of f2 multiplied by 5 all over the hypotenuse, which is still 13. Okay, so solving this, f2x would be 260 times 12 all over 13. That would give us 260 by 12 divided by 13. That's 240 newtons, or still positive 240 newtons, and it's going to the right. For f2y, that would be f2y is equal to negative 260 by 5 over 13. So that's negative 260 by 5 divided by 13. That's equal to negative 100 newtons, or that's 100 newtons going down for f2y. So the answer for this one, let me shift the page. So 240 and 100. So for force f2, the Cartesian form would be 240 I, that's the x component, minus, so the y component is negative, so that's minus 100 j. And let's enclose that and write the unit. Okay, so our task is just to express each vector in its Cartesian vector form. So let me write here, these are our answers, and let me just rewrite here f1, which is let me go back. F1 is negative 100 plus 173.21. So that's negative 100 I plus 173.21 J. Newtons. Okay, so these are our final answers. So the problem didn't ask us anything about getting the resultants, but if you want the resultants, you can just add the components going in the same axis, so the x-axis and the y-axis. But if you want to see the resultant, so the resultant for this would be this is 240 plus negative 100, that would be 140. So again, it's not really asked in the problem, I just want to show you how to write it when you have your Cartesian vector notation. This is negative 100 plus 173, so that would be positive 73. 73.21 J newtons. So this is your resultant for this two force vectors, and let's also try to find the magnitude of this. So your resultant, again, this is not really asked in the problem, but for the sake of illustration, I just want to show you how to do it. So we have 140, that would be the square root of the sums of their squares. So that's 140 newtons squared plus 73.21 newtons squared, and take the square root of that. So we have 73.21 squared plus 140 squared. Take the square root of the answer. You have approximately that gives you 157.99 newtons, and we can find the angle by the arctangent of the absolute value of, since these are both positive, this is already positive, of y all over x. Okay, so the angle would be 40 27.61 degrees. 27.61 degrees. Okay, so if you can imagine, this one would be again, I just want to remind you that this is really not part of our solution, just an extension of the problem, since we're still studying how to operate on these vectors. Okay, so as you see, both the components are going in the positive direction. That's why. So let me use this. So the component in x is here, and it's 140. So in the component in y is here, and it's 73. So most likely your resultant force would be here. Correct? So let us write down the values. So this is, oh sorry, let me undo that. So here Fx is equal to 140 newtons, Fy is equal to 73.21 newtons. This is the resultant force, which we've solved as 157.99 newtons, and the angle we are looking for is this one, which is, oh sorry, I made, this is actually Fy, sorry, and this is Fx. Fy, Fx, I interchange it, so let me just erase that. So this will be, this one is 73.21 and Fx is 140. So sorry about that. So that's 140. Okay, so this angle is the tangent of this angle is equal to the opposite over adjacent. So that's Fy over Fx. So in this case, the angle is this one. Okay, this is 7.6 degrees. Okay, so if we are going to be asked what is the resultant of this force, of these two forces, this should be our final answer. Okay, it should be a drawing. Okay, so since we're looking for vectors, we want to see the magnitudes as well as the direction and the line of action. That's why our answer should be this drawing. Okay, so for this one, this is our final answer. So we have, this is the first one, 200 newtons. This is 200, F1y is 200 cosine 30 degrees, and F1x is 200 sine 30 degrees. So this one is negative. So for F2, the same thing. F2x is 12 over 13 times 260. F2y is 5 over 13 times 260, and this is a negative number. So for our next sample, we have a link, this one, this link, and is subjected to two forces, F1 600 newtons and F2 400 newtons, which are oriented as shown. So F1 is in the first quadrant and F2 is in the second quadrant, and these are the direction. So F1 is 30 degrees from the x-axis and F2 is 45 degrees from the y-axis. So our task is to determine the magnitude and direction of the resultant force. So pretty much we will be doing the same thing as the first sample problem, but from the first sample problem, it is not really what is asked. We just try to illustrate how it's done, but this time the problem is asking us for the resultant force. So the problem pretty much looks like this. So let me write it down as the given. So, oh sorry, okay, let me erase that. So given, this is our given. We have here F2, this is 400 newtons, and F1, this is 600 newtons. Okay, so you can write down your given this way by drawing the free body diagram or of this of the system. Okay, so this is 30 degrees and this is 45 degrees. So be very careful where you write the angles. So pretty much this side would also be, for this one, this would also be 45 degrees. For this one, this would be 60 degrees. Okay, so these are our given. So let me check that if that's correct. Yep, we have the correct drawing. So let's see what is required. So the problem is just asking us the magnitude and direction of the resultant force. So what is the resultant and what is its direction? That is what's the problem is basically asking us. Or this is magnitude and direction. That means we're looking for a vector here. Right? So let's start our solution. So in order to arrive at the Cartesian vector form of our resultant, we first need to express both our given forces into their own Cartesian vector form. Is that right? That makes sense. So let's go for first one, which is 600 newtons. We look for fx, which is f1x, which is positive, as well as f1y in this case will also be positive. So let me also write here the components we are looking for f2. So this is f2x, it's clearly negative, and we also have I won't repeat the arrow since they are going in the same direction. So f2y. Okay, so for f1x, let's write the equation. It will be positive, right? And that would be equal to f1 or 600 newtons multiplied by, this is 30 degrees and this is an adjacent side, so that would be cosine of 30 degrees. So that's 600 by cosine 30 is again square root of 3/2. So we have f1x approximately 519.62 newtons. That's approximately, okay? So in your calculators, please store this value, okay? So this is the answer. This is, I'll store it in my calculator. Okay, this is an approximate value. So let's go for f1y. That would be equal to, we're looking for f1y and it's in the opposite of the angle, so that's 600 newtons multiplied by sine, opposite over adjacent, so opposite 30 degrees angle, sine 30 is 1/2, so this is 300 newtons. So just for just to begin, I will write here the Cartesian form of the first vector. That would be 519.62 I plus 300 J newtons. So we have the Cartesian vector form for the first vector, force 1. Now let's go to force 2, which is 400 newtons. We are looking for F2. In the x direction, this is clearly negative. So that's negative 400 newtons multiplied by this is, in this case, the given angle is here, this one, and it's 45 degrees. So F 2x happen to be opposite that, so that would be sine of 45. But you know well that doesn't matter if we use cosine 45, it would be the same. We have another 45 angle here, and that would be adjacent this component, so we will use cosine there. But then again, please be very particular, because not all the time this would be 45 and 45. This might be 50 40, 60 30. So just stick to the correct convention. Okay, so the sine 45 is equal to, this is negative 400 newtons multiplied by the square root of 2 over 2. So we have here negative 400 times square root of 2 or sine 45 that's negative 282 point approximately 84 newtons, or we can write it down as 282.84 newtons and going to the left. Okay, so again, you store this value since we rounded off here. So for f2x would be, sorry, f2y, that would be positive, so that's 400 newtons. This time it's cosine 45, which is the same thing, just positive. So 400 newtons square root of 2 over 2, that's equal to the same thing, approximately 282.84 newtons, or 282.84 newtons, and it's going up. So now it's time to write the Cartesian vector format for F2. And we have a negative value for the x component. Oops, let me undo. 22.84 I plus 282.84 J newtons. Okay, so now both our vectors are expressed in the Cartesian vector form. So the things left to do is to find the resultant, and we will be doing that by scalar algebra. So for the resultant force, the resultant vector, let us write the x components. So for F1, this is F2, the x components. Let me do that by having a table, and the resultant would be here. Okay, so for F1, the x component is 519.62 and y component is 300. So for F1, that's 519.62 newtons. For the y, that's 300 newtons. So for F2, that's the same thing, just different signs. Negative 282.84. So that's negative 282.84 newtons and positive 282.84 newtons. So now we will do scalar algebra. That's 519.62 plus negative 282.84. The x component for our resultant force would be this one is 236, approximately 0.77 newtons. So let me store that answer. Store in another value. And this is 300 plus 582.84. That would just be 582.84 newtons. Okay, so here, writing our resultant vector in its Cartesian form, that would be, this should be part of our final answer, right? The Cartesian form of our resultant vector, that would be 236.77 I. So see here, these are both positive values, so plus 582.84 J, that be in newtons. So we need to look for the direction angle, which let's call it theta. So theta is again equal to the arctangent of the Fy component over the Fx component, or let's write it down as 582.84 over 236.77 newtons. Okay, so let me plug that in my calculator. So I have okay, so that would be, oh, okay, so let's solve for the angle first, and then we find the magnitude of this. I'm sorry, I skipped the magnitude. We went directly to the angle. Okay, so that's, let me do that again. Alpha d divided by alpha. So I have here 67.89 degrees. So this is our direction angle. Let's find the magnitude of the resultant force, which is equal to the square root of the x component, which is 236.77 newtons. That's squared plus The same thing for the y component, 582.84. Okay, so plug this in the calculators. So we have, so in our, the calculator answer would be 629.1 approximately Newton. So this would be our magnitude. So let us write that down as, let's compile it as our answers. So what we need is, since we see that both the components are positive, we will be drawing it only on the first quadrant. So let's draw a quadrant here, which is the positive axis, and this is our vector. So it's about 67.89. So let's try to be realistic here. So it's somewhere going here, right? So our components would be here in the y, and x somewhere there. Okay, so our resultant force is Fr, we solved as 629.1 Newton, and this angle theta here, so we solve this angle by finding the arctangent of the opposite over adjacent. Since this is your Fy, its opposite, that's 582.84, and your Fx is 236.77 newtons. So we found the angle by dividing opposite over adjacent. So this is our angle, the angle which is made with the x-axis, and that's, we saw that as 67.89 degrees. Okay, so this is our vector. We can see its direction, the angle, and also we have solved for the magnitude of it. What remains is to write it down in its Cartesian vector format, which is f r. So this is what is expected of you in your solutions. Okay, so the drawing of the vector as well as the Cartesian vector form. So that's just 236.77 I plus 582.84 J. Newtons. Alright, so this would be how we will be writing our final answer. Okay, so for our source, it's still our reference book, Engineering Mechanics Statics. That's the 2015 edition. The author is Russell Hibbeler, and this lesson is found in page 33 up to 37 of that. So thank you for your time, and I hope that you understand the lesson for today. And if you have any questions, don't hesitate to contact me through my email. And always practice problem solving. There are plenty of problems you can work on our reference book, so that this operations in force vectors will be easier for you. So our next lecture would be we'll be going 3 dimensions. Okay, so see you then, and good luck. Thank you for your time.